Welcome, everybody in the lecture hall on Zoom from the future. Today, we will be looking into white column stores as we started last week. And it will be a bit of a warning, a complex lecture. It's one of the most complicated lectures of the entire semester. However, we'll take the time to go through it. The reason it's complex is that it's going to be about the physical layer of HBase, but it has plenty of very, very interesting features. And in fact, these features will be common to MapReduce, Spark, and so on that we will see later. So it's not just for the purpose of HBase, but also for the coming weeks that this is particularly important. This is why I'm going to take it slowly, drive you through all of this. The key word actually for this physical layer will be batch processing, right? So until now, we've looked at parallelism with the blocks in HDFS. And now we are going to look at batch processing, what it actually means and how it's done on the physical layer. Before we start, I'm going to ask you a question just out of curiosity for last week. There you go. Which is better, XML, JSON, totally equivalent, or it depends on the use case at hand? Realizing that the sun might be interfering with the slides in the room. Maybe I can close. Is it the front ones or the back ones? It seems to be from this side. Let me try this. If it doesn't work, I'll try the others. No, that's the other one. Yes, it's coming from this side, right? Yeah, I think this is it. While you answer the question, yes, so the sunlight is now going to look much better. And then we'll look at your answers. All right, is it better now? Yes, okay. So now let's look at your answers. So the majority is saying that it depends on the use case at hand. And yes, this is the one answer that I like to hear the most. It depends on the use case. The idea is that they are both based on arborescent data models, 3 data models, denormalized data. And in fact, next week, I will tell you many details about them at the on denormalized data at the data modeling level. So we'll see they are actually very similar. Totally equivalent, almost. There is one use case where XML stands out compared to JSON, and that's publishing. When you want to store scientific papers or books and so on, then this is the one use case where XML shines compared to JSON. The reason is simply that XML allows you to mix text with tags. This is the one reason. But if you want to store data sets, normalized or denormalized, then both of them will just work. And it does not really matter. So there is now a rising number of people who use JSON. XML has the advantage of being older, so it's more enterprise ready. There are more libraries, so the companies tend to trust it a bit more, but JSON is catching up with the technologies. All right, but again, the answer I like the most is it depends on the use case at hand. But of course, you are free to prefer JSON or to prefer XML. I see there are more people who prefer JSON, and that's totally fine. The simplicity of JSON makes it indeed an attractive solution. All right. And the third answer, you got it right, that they both represent trees, right? And we'll cover this next week. Yes, and I did mark that one as correct. All right, so now I'm getting back to the slides. And hopefully we'll be exactly where we were. Yes. All right. So this is not where I want to be. It didn't load the right one. normally this one. Let's see if it does a better job this time. What's going on? Courses. I'm not sure exactly. Oh, maybe it did not save. I wanted to start directly where we left off. That's why. So let me just do it now, and then we'll project. Okay. I probably forgot to save when I fast forward it. All right, now I am where I would like us to be. So I always start every lecture, every coverage with the logical level, right? So we'll go ahead. I already started a bit with the logical level. We start with that, and then we will see how it's done on the physical level, right? This is called data independence, right? So first, let's focus on the logical level. So on the logical level, the data model is relying on bigtables. In fact, that's why it's called Bigtable, the technology when Google came up with it. And then HBase is the open source version that is called HBase. So it's a bigtable. And one of the columns is special. This is called the row ID. This is based on a key value model, meaning that each row is uniquely identified with a row ID, which is a particular attribute, a particular column. If you remember relational databases, that would be called the primary key, right? So the row ID is a primary key because it uniquely identifies the row that you're speaking about. A major difference with the kind of tables you would see in a relational database system like PostgreSQL is that in PostgreSQL, you can have multiple columns that act as a primary key, multiple columns, right? But here it's really just one column. It has to be one, and this is the row ID column. Next, there is something that also makes it a bit stand out from relational databases. It is that the columns are just not, columns. They are actually organized in families. So there is here the purple family, the yellow family, the red family. So we have column families. Why do we have that? Well, this is in order to scale. Because in a relational database system, you have a limitation on the number of columns. You can typically go to 256 columns or something like that, but not more than that. So if you want thousands of columns or millions of columns, obviously it would mean that it's very sparse. A lot of the cells will be empty. But if you want millions of different columns, it will not work, and we need a different design. This is achieved by having column families, right? And we'll see on the physical layer, this is because the column families, they are stored together. That's the main reason. All right. Something more about the column families is I told you that we denormalize things when we store data in big tables. By this, I mean that we might have had, let's say, 4 or 5 relational tables in PostgreSQL if we had done things according to typical database design, right? Every table should account for one particular type of thing you're talking about. But in the case of HBase, we denormalize, and that means that we actually join everything together as a single table, right? So this is what we get. We have everything directly available as a single table. Obviously, there's going to be a bit of redundancy in there because we've just put everything in the same table. For example, if it's a list of, let's say it's a list of people listed in the purple part, maybe in the yellow part, it's going to be addresses, mailing addresses. But obviously, if some people live at the same address, then the addresses will be duplicated, right? There will be multiple addresses for the same people. This is an example of denormalization, right, with the Boyce code normal form. Okay, but we do not denormalize to the point that we get trees, right? We still have a table, tabular model. Okay, so these are the column families. And again, we might have in the purple part people, and in the yellow part maybe products, and in the red part orders, and so on. But it's all organized, pre-joined, all together in the same table. Next, in addition to the column family, there's obviously the name of the column. so the name of the column family plus the name of the column together identify a column, right? It's the same as first name and family name, right? You could, in fact, compare the column families with namespaces if you want, but it's not so important. Okay, so now I use the Latin characters for the purple family. I use the Indo-Arabic numbers for the yellow family, and I use Roman numbers for the red family, right? Just to show you. All right, so far so good. Is everybody following? Okay, so this is the design. Again, it's a table, but the main difference with PostgreSQL is we have a single column that uniquely identifies the row, and the columns are grouped in column families. All right. The next thing that is interesting, and this is also new compared with PostgreSQL, is that you can make up new columns on the fly. As the database evolves, you can just create new columns just like that, right? Not new column families, new columns in existing column families. Now you could tell me, okay, yes, but we can do the same in PostgreSQL, right? I can also instruct PostgreSQL to add a column to my relational table. Yes, but in PostgreSQL, this is going to be slow. If you want to add a column to a very large table, it's not the kind of trivial operation that just happens in a millisecond. No, it's going to take time because it needs to rewrite the entire layout on disk and so on. But here, adding columns is supported seamlessly. You just make them on the fly, and it doesn't even have any performance impact, right? So it's actually really, really good at coming up with new columns the whole time. So when do we have new columns? Well, maybe you're just going to insert a new row in your table, and that new row will have columns that did not exist before, and that's absolutely not a problem with HBase, right? So you can just make up new columns as you go just by inserting them in new rows or in existing rows. What you cannot do so easily, you can, but it's going to be slow, is add new column families. So if I want to add a green or blue column family, it's going to take some time to do. It's not going to be as quick as adding a new column in an existing family. For whom is that clear? All right. Now, one more thing. So I'm basically basing my explanation on a contrast with PostgreSQL and relational databases, right? You might remember that PostgreSQL has data types, right? In a column, you can have integers. In another column, you can have dates. In another column, you can have texts. In another column, you might have binary and so on, but you have types in every column. And this is called domain integrity, right? When you ensure that in every column, you have a specific data type. Well, HBase could not care less about types. For HBase, everything is just binary. Everything. So the row ID is just a bunch of zeros and ones. The names of the column families and column names and so on, these are all a bunch of zeros and ones. Everything is just a bunch of zeros and ones, right? So of course, as the user of the system, you probably are using a high-level programming language, and it's going to automatically create these zeros and ones out of text, right? For example, if you just call it A or B or C, it's going to be using some encoding of A, B, or C in bits. But HBase does not know about anything being an integer or a string or a date. It just doesn't know. It's just binary. So in a way, you push the burden of dealing with this to the user, right? Since HBase is not doing it, it's you as a user who has to deal with it, right? So we would call it a lower level than PostgreSQL for this reason. But of course, you as a user, if you use Java or Python to access the system, nothing prevents you from actually putting integers or putting dates and so on, as long as you convert them to zeros and ones, right? And there are libraries out there that will even do it for you if you want. But HBase just doesn't know about it. So for HBase, everything is just a bunch of zeros and ones everywhere. Okay. Why do we have these zeros and ones? Well, this is in order to support something that, again, we cannot really do efficiently with relational database management systems. In a typical relational database, the cells are rather small, right? you put, I don't know, a number or a date or a short string and so on, but it's not meant to put huge documents, right? You can, if you do it, PostgreSQL will allow it. It has all kinds of ways that it's going to deal with it, but it's not the primary design of relational database to deal with very large content in a single cell. HBase has no problem with that. The sweet spot can do more, but the sweet spot is that you can go all the way to 10 megabytes per cell. And again, it's just zeros and ones. So that just means like roughly 80 million zeros and ones in the same cell, right? This is a lot, right? Compared to just storing a single integer or a single date. This is a lot. And what do we typically put in these cells? Well, you can actually put whatever you want, but a good use case of things that you put in there is, for example, some HTML page, right? A blog post, an HTML page, or an XML document, or a JSON document, right? So you could have some row IDs, and then in a column, you just have JSON documents or XML documents up to 10 megabytes in size, right? And what HBase gives you is a very efficient way of retrieving these documents by key. Right? For whom is this clear? All right. But today we will not look at these cells, right? I'm just saying you this is XML, this is JSON, this is whatever you want. But today we don't care what there is in there. We will care when we actually query the data. But today it's just whatever. Could even be a picture, a video, whatever you want in a cell. All right. Okay. So this is the model. And again, I compared it with PostgreSQL, right? So again, if I summarize the differences, there is a single column that is the primary key called row ID. There cannot be multiple columns. The second difference is that the columns are grouped in families. The third difference is that you can make up new column names within existing families very easily and efficiently, right? Another difference is that it doesn't know about data types and everything is just in a binary format. So you push the burden to the user of dealing with this. And finally, we can very efficiently store large cells, and it's recommended to go to 10 megabytes and to avoid going higher than that. All right. So this is the model, right? This is the model. Now, when we have the model, we want to use it and query it. This is still the logical level, right? This is now how the user interacts with HBase. There are four different ways that you can interact with HBase. And as you will notice, this is not SQL. This is another difference with relational database management system. It doesn't support SQL out of the box, SQL. Instead, it supports lower level primitives that should also be primitives we've already seen with S3 and cloud storage, as you will see. The first one is get. What does get do? Well, if you give a row ID, get will give you the entire row, right? This is what get does. So it looks up the key, the row ID, and gives you the contents of the columns associated with this row ID. You can also instruct HBase to only give you the yellow columns, the yellow family, right? Or only the yellow and purple families, right? You can also specifically select families to not get everything, but just partial content. That's also completely fine, right? This is get. Then you have put. Put means that you give a row ID. It's typically going to be a new row ID if you want to insert a new row, but it can also be an existing one if you want to overwrite some value, some values or some value. So you basically say, here's a row ID that I want to put data in, and here are values for the purple column and for the red column, for example. And then HBase will either insert a new row or add the data or overwrite the data in these columns. This is when you can make up new columns. You can absolutely say insert row ID, I don't know, 206, and then make up some column D and E and and 3 and 4 without any problem, right? You can absolutely make up new columns that don't exist, right? Just not column families. Column families, you need a special command that takes more time. But the columns, yes. So this is get, this is put. Then we have scan. This is the one we didn't have in S3, right? In S3, we had get and put and delete, as we will see. But scan, we did not have. What is a scan? It means that, for example, you want to go row by row on the entire table, right? So you iterate on the rows one by one, and you just make your way through it. You have some way in the API to do the iteration, or on the command line on the shell. And this is just going to scan the entire table, allowing you to read the rows or do something on the rows one by one. Now, in a scan, it's just like the get or the put. You can scan, for example, just the yellow family. That's fine too, right? Then you don't read the purple and red families. That's totally fine. You can also decide to scan just an interval, right? Maybe you don't want to scan the entire table. You only want to scan everything that is in between 1E0 and 22A, for example. That is fine too, right? So here we are scanning both just an interval of row IDs and just a specific column families, okay? And the fourth one is get, put, scan, and you can guess it. On Zoom, this is one we have in S3 as well. Delete, right? You can delete. So if I give you a row ID, so 204, then you can just delete what there is in there. Okay. So this is it. You can get, you can put, you can scan, you can delete. That's it. It's that simple, right? So again, this is low level. First, it's only bits, zeros and ones. We don't have data types. Second, we don't have SQL. We can just get, put, delete, and scan. But don't worry, because some people added back SQL on top, right? It's just made on a higher level. So you have a way to actually plug back SQL in there. Okay. Some terminology to clarify things. This key value model that I told you about, it's something that we will see during the entire lecture, the whole time, almost every week. We saw it in cloud storage in S3. We saw that the bucket ID plus the object ID, that's actually a key, right? And then the object or the file itself, that's the value. This is a model. This is a logical model. It's also called a map. Computer scientists also call it a map. It's just a model. In HBase, we also have a key value model in the sense that the row ID is the key and the value is just the rest of the other columns. For whom is that clear? All right. So this is the key value model. Second, you might have heard of column-oriented storage. This is something that should not be confused with white column stores. What does it mean, column-oriented storage? It was actually quite a hype 15 years ago. Typically, when you have relational data in PostgreSQL, if you look at how it is stored physically on disk, PostgreSQL is going to store it row by row. One row, then another row, then another row, and so on. Column-oriented storage does it the opposite way. It's storing column by column. So if you look at the disk, you will see all the first column, and then all the second column, and so on and so on. So this is called column-oriented storage. It has its advantages, right? If you have a lot of columns and you're only looking at a few of them, then in fact, storing column by column might give you a performance improvement. It does not change anything to the way the database works, right? Seen from outside, you still see a relational database. It's a physical detail. So this is called column-oriented. But as we will see, when we look at the physical layer, here it's a wide column store, because we do not store column by column, we store column family by column family, right? So we still have the purple ones, the yellow ones, the red ones together, but we will look at the details of that, right? So we would not say that HBase is column-oriented storage because it's not column by column, but it's a wide column store, and the wide means that it can have a lot of columns organized by families, okay? And why do we call it a store and not a database? Because we could have said wide column database, right? Or database system. Well, typically, in terms of terminology, what the database people do is that they reserve the term database management system for the full-flown product with many features. So when you say database management system, you typically expect a rich data model with data types and SQL and so on, maybe even transactions, and so on. So when you say database system, you really expect that big product that completely isolates you. But for the systems that are simpler and that do not go all the way to giving you SQL and that full complex product, they call it a store, a data store, right? That's a common term. So why do we say it's a data store? That's for all the reasons I told you. I told you that it doesn't have data types. The data is just binary. It doesn't have SQL. Rather, you have this get, put, scan, delete, right? That's rather low level, and so on and so on. So that's the reason it doesn't enjoy the name of database system. Rather, we call it a data store, a white column store. Does it make sense? Right? So again, when you say database management system, you expect the fancy, expensive product that has all the features. And when you say data store, you expect a system that is on a lower level. It's simpler in design, but it pushes the burden on you, right? To basically compensate for the features it doesn't have. All right. Now to give you a few names, there is Google Bigtable, that's the original one. HBase, that's the one we take as an example, but most of what I'm telling you is actually applicable to all of them. Cassandra is yet another one. That's the one by Meta, back then Facebook. Yeah, but they are more or less the same. There's a few minor differences. I mean, if you later use them, you will see that they will be very easy to learn from what we've covered in the lecture, right? You just need to look for the diff. There's plenty. You know, when you want to know the differences between two systems, you can just Google for it, right? And you will typically find pages that summarize the main differences, but you will see that it's minor. And when I'm saying Googling, I could almost say now ask ChatGPT, because it seems that things are going quite fast these days. But basically what I'm saying is that it doesn't really matter which one you use. What we cover in this lecture is really generic. And I'm just using HBase as a convenience so that I can rely on a specific product. Okay. So now I am about to enter the difficult section on the physical layer. We're going to take all the time we need in order to go through all of this. I'm going to make sure that you're following. But before that, you can ask questions. Is anything unclear about the logical model, what we've covered so far? The row IDs, the columns that you can make up on the fly, the column families, get, put, scan, delete. It's all good? Who is ready for the physical layer? All right, then let's go. After I remove the antivirus pop-up. Okay. So let's go for the physical layer then. So let's go back to first the logical model where we have the row ID, the families, and so on. As we've seen in previous weeks, when something doesn't fit on a machine, what do we do? Because that doesn't fit on a machine, right? We are talking about petabytes of data. What do we do? Maybe on Zoom? Anybody knows on Zoom? What did we do, for example, in HDFS? With a petabyte file. Yeah. Yeah.
We scale out.
Yes, we scale out. And scale out means plenty of machines. So how do we then scale out this?
Probably by cutting it in different columns and do it on several machines.
Exactly. We cut it into pieces, just like a pie, right? So we are indeed going to cut it. So the fancy name, if you want to sound fancy, that's going to be partition. We partition it, but it essentially means what you've just said. So how do we cut that pie? Well, if you've looked at these fancy cakes that are rectangular, typically we don't cut them just horizontally or vertically, right? You know that, I'm sure you have eaten these, right? So you cut it both horizontally and vertically. We are going to do the same thing right here. We are also going to cut this pie horizontally and vertically. So first, let's start cutting it horizontally. We are going to obviously preserve the rows, right? Why would we cut in the middle of a row? So we are just going to look at the entire rows. So there is something called a region that is an interval of rows. More precisely, it's an interval of row IDs, right? So obviously, in order to do that, I need to do something. I need to require that the row IDs are sorted. That's a requirement. The row IDs are sorted. if they are sorted, then I can define a region by saying this is the minimum row ID of my region, and this is the maximum row ID of my region. For example, between 5 and 10, right? So I have the region between row ID 5 and row ID 10. In order to, this is probably because computer scientists love doing this, maybe mathematicians as well. When I say 5 and 10, I don't mean including 5 and including 10, right? I mean including 5 and excluding 10, right? So it's, if I say from 5 to 10, it's going to be 5, 6, 7, 8, 9, but not 10. So that's called the minimum inclusive and the maximum exclusive. Why do we do that? Well, it's because the maximum exclusive then will be the minimum inclusive of the next region, right? So it's just easier to specify that way, right? Because then you just specify the minimum inclusives of all the regions, and that fully defines your partition. For whom is that clear? Right, so minimum inclusive, maximum exclusive. Okay, so this is how we cut the pie horizontally. And we also cut it vertically. Guess what? By column families. That shouldn't be really a surprise to you. There is a question over there. Oh, I'm not sure how it's done specifically here, but I would just use the plus infinity or, you know, or the max integer value, right? Because that's just used for a comparison, right? So you, if you put whatever is higher than the maximum row ID, then that takes care of it. No, this is not a ring. This is really just a line, more like a line, right? Yeah. So you can either think of it as the max integer for the region that is at the bottom, either the max possible integer or plus infinity, or maybe you can also decide that you leave it empty, and if it's empty, it means that it's all the way to the end, right? Yeah, but that's a good question. It's nice to be thorough and to think about these things. All right. So this max integer, by the way, in a language like Java, I don't know Python, probably also, but in Java, for example, you have a constant for every type, integer, long, and so on. You have a constant that gives you the minimum and the maximum integer that you can have. So you can just use that constant and you directly get the maximum integer. A common assumption is basically that you're never actually to use it for data. You typically use it when you do comparisons to just catch everything. All right, so we cut the pie horizontally, we cut the pie vertically, and what we get is then, I have room here, yeah. So what you get is, here, that is one partition. Here, that is another partition. Here, that is another partition. And maybe, and now if we use max integer here, that would be another partition, yet another partition, yet another partition. And maybe if we assume we go on the beginning here, another one, another one, another one, right? So for example, you could imagine that here you have 9 partitions, 3 by 3, right? So one per column family for cutting vertically, and one per region for cutting horizontally. All right. Now that we have cut the pie in order to spread it in partitions, that would be just like the HDFS blocks. We need to look at the architecture in the sense of how are the machines organized in my cluster. So I have this data center, I have this big room with 1,000 machines. How do I organize it? Well, I have good news, because this is exactly the same thing as we've been doing with HDFS earlier, right? Same procedure as every year, James. So in HDFS, you might remember that it was a centralized architecture. We had a node that coordinates everything. That's the name node. It has the file namespace and the mapping from the file to blocks, the locations of each blocks, and so on. And then we have the data nodes that store the actual data. Who remembers that? We've seen that, right? Okay. Well, the good news I have for you is that this is the same thing for HBase. They just have different names. We call the coordinator nodes the Hmaster, and we call the worker nodes the region servers. Right. What's more, and that actually makes it actually easy, is that these are the same machines. So the Hmaster and the name node run on the same machine, and the data nodes and region servers also run on the same machines. If you want to be very precise, who knows what a process is in a computer? Okay, so I'm just going to say, just so you know, but you don't need to worry too much about this. Let me put it that way. On your laptop, you probably are running multiple programs at the same time, right? Maybe you have Excel open, you have Word open, you have PowerPoint open, you have IntelliJ open, you have a Jupyter notebook open in your browser. These are called processes, these programs. Well, you can imagine that, for example, on the machine that is the coordinator machine, you have one program that is the Hmaster and another program that is the name node, right? So very commonly, when people talk about the Hmaster or the name node, they typically mean the machine. But if you want to be really precise, it's not the machine itself. It's a program running on that machine. So you basically have one machine that runs the program name node and the program Hmaster. And then you have 1,000 other machines that each run a program that is the data node program and a program that is the region server program. Does it make sense? Okay, so let's put it that way. So now I'm going to do the same thing I've been doing for HDFS, and I'm going to first go into the details of the Hmaster coordinator node, and then we'll go into the details of the region server programs. Okay. Now, keep HDFS in mind, because you can really make a parallel with HDFS. The Hmaster is the nodes that you need to contact for high-level operations. It's the same in HDFS, right? In HDFS, if you want to create a directory or delete a directory or create a new file and so on, you have to go to the name node, right? Well, in HBase, if you want to create a new table or delete a table or add a column family or whatever, you also go to the coordinator nodes, the Hmaster. So these are called the DDL operations. You might remember that DDL means data definition language. It's whenever you define the high-level shape of your data. All right. So this is the first thing that the Hmaster does. It's the responsible, that's the place where you create and delete all your tables. There is another thing that the Hmaster is doing. It is assigning the regions to the region servers. If you look at the row IDs here, we saw that they are horizontally partitioned, right, with this min inclusive and max exclusive intervals. So we partition horizontally the whole system, and we assign every one of these regions. These are called regions, the horizontal layers of the cake. So we call them region, and each region is assigned to one region server. And now you probably understand why it's called region server, right? Because it serves regions. All right. So you see that, for example, this row ID right here, that's a row ID, is managed by this machine right here, this region server process, right? This region here, from here to here, is handled by this region server right there. This region here, the purple region, is handled by this. Oh, I got the colors wrong, should have swapped. Anyway, it's handled by this region server right there, right? So every region, every horizontal layer is assigned to one of the region servers. But now you're going to tell me, yes, but we also slice the cake vertically, right? Here. We had these vertical slices. So why do we not assign partitions to the machines? Well, we assign entire regions, and that means that here, what is in green, these are 3 partitions, right? For this specific region, that's 3 partitions. These 3 partitions will be taken care of by the same region server together. They will still be stored separately. You know, there will still be partitions, but the process responsible for them is the same one, right? So in order to attribute the partitions to the physical machines, to the region servers, we only consider the horizontal slices, right? But again, it's still also sliced vertically within the region servers. For whom is that clear? All right. So again, to be clear, what I call a partition would be, there would be 9 of them, right? So this is a partition, this is a partition, this is a partition, this is a partition, this. There are 9 of them. What I call region is the horizontal slice. This here is a region, this here is a region, this here is a region. There would be 3 of them, right? So this is the reason here, when I was talking about regions, I only divided horizontally, right? Now I have 1, 2, 3, 4, 5, 6, 7 different regions. Maybe there are 4 column families. So then that would be 7 times 4, that's 28 regions, 28 partitions, 28 partitions. But I have 7 regions of each 4 partitions, and the 4 partitions of every one of these 7 regions are all handled together by a region server, right? Just repeated the same thing, but I just want to make sure that it's very clear. So we assign the regions to the region servers. There is one question that you did not ask, but I will still answer it. It's in HDFS, you might remember that every block was stored in 3 different data nodes by default. 3, it's replicated, right? But here, it's only 1 region server. So it seems like we are not replicating things. That seems a bit risky, right? If we are not assigning a regions to multiple region servers. The one thing to understand here is that this assignment here is only a responsibility assignment. It doesn't mean the data is not duplicated. This is only a responsibility. We are only saying, you here are responsible for the blue region. You here are responsible for the green region. This is what it means. But the data in the end, as we will see in the second hour today, the data is actually stored in HDFS as a physical layer. And because the data is stored as HDFS files, it will be duplicated by HDFS. So you can consider that, I don't know, HDFS here is a service provider. HDFS guarantees you that it duplicates the data, so you don't need to take care of it. So this is why here we don't care about duplicating the data. It's done by HDFS anyway. And all I need to say is this region is taken care of by this region server. If the region server fails, no problem, another region server will take over. It's anyway on HDFS, the data. So you just switch the responsibilities. All right. Now, what could happen as you use HBase and you keep inserting and inserting and inserting data into the table, remember that the regions, they are defined with this minimum and maximum. So then what happens if you then start inserting a lot of rows in the same interval? And then that region is growing and growing and growing to the point that it becomes too much to handle as a single region. So what's going to happen then is that the region server in charge of this region is going to split the region. Instead of one region is going to be 2 regions, so it's going to split each partition within that region into 2 partitions, right? So in that case, it's creating a yellow region, and the blue region, we keep the color, but it's basically splitting it into 2, but it's still responsible for the 2 regions, right? It's just splitting it, but keeps dealing with the region, right? So this is the first thing. The region servers can split the regions when they become too large. The second thing that can happen as this continues to grow and grow, then it might be that a region server will suddenly be overloaded by too many regions, right? Some region servers might have a few regions, and then you have a region server there that has too many of them. What then happens is that the Hmaster can reallocate responsibilities. It can say, okay, now you're too busy, you're too overloaded, just hand over this and that region to this other machine that has less work to do, right? So this is a reassignment of the responsibilities, right? So this is, in that case, for example, you might see the third region server here has 3 regions to take care of. The fourth one has only 1 region to take care of, right? So this is not enough. So we rebalance things a little bit and we say, okay, now the yellow region is from now on going to be taken care of by the 4th region server. The data itself is on HDFS, so we don't care, right? It's only an assignment of responsibility. It's now you stop dealing with the yellow region and you, sir, start dealing with the yellow region. Okay. So what did I do here? Oh, yes, I made one crash. So on that picture, let's keep it as a cliffhanger because it's nice. So cliffhanger, this crashes, what do we do? Now we take a break and we'll answer this in 15 minutes.